NASA permanently blinded one of the greatest machines humanity has ever built on purpose. And the last thing it saw before they killed its eyes forever changed how every human being on this planet thinks about where we live. We are talking about a spacecraft the size of a small car launched in 1977 that spent over a decade crossing the entire solar system. And on one single day in February 1990 it turned around, looked back at everything it had passed, and took 60 photographs. 60. That is the entire visual legacy of the most distant photography session in human history. And 34 minutes after the last shutter click, NASA engineers sitting in a room in California began the process of permanently erasing the spacecraft's ability to ever take another picture. Not because something went wrong, not because of a malfunction. They did it deliberately. They chose to blind Voyager 1 because it was the only way to keep it alive. What those 60 frames captured before the lights went out forever is one of the most important and most humbling stories in the history of human exploration. And clears throat. Most people have no idea how close the whole thing came to never happening at all. Voyager 1 launched on September 5th, 1977. The entire mission was built around something extraordinary, a planetary alignment that only happens once every 176 years. When the planets line up in just the right configuration, a spacecraft can use the gravity of one planet to slingshot itself toward the next, gaining speed without burning any additional fuel. Scientists call it a gravity assist. It sounds elegant and simple. In practice, threading a machine through multiple gravity assists across billions of kilometers of space, with 1970s computers and 1970s hardware, was one of the most ambitious engineering undertakings in human history. Voyager 1 swung past Jupiter in March 1979 and captured images that left scientists and the public completely speechless. The Great Red Spot, a storm larger than the entire Earth that had been raging for centuries, was photographed up close for the very first time. Jupiter's moon Io turned out to be the most volcanically active world in the solar system, something nobody had suspected before Voyager arrived. Europa showed a cracked, icy surface that suggested a liquid ocean underneath. Every single image was a discovery. Every frame rewrote something that had been in the textbooks. Then Voyager 1 reached Saturn in November 1980. The rings, which from Earth look like a flat disk around the planet, turned out to be an impossibly complex system of thousands of individual ringlets, each one following its own orbital path. Shepherd moons were discovered, tiny worlds whose gravity herds the ring particles into their lanes. Saturn's moon Titan was found to have a thick orange atmosphere, so dense that the cameras couldn't see through it to the surface below. Again, completely unexpected. Again, science rewritten in real time. After Saturn, Voyager 1 was flung out of the plane of the solar system entirely. Its trajectory after the Saturn flyby sent it above the ecliptic, the flat disk where most of the planets orbit at an angle that made visiting Uranus or Neptune impossible. The planetary mission was essentially over. Voyager 2, the twin spacecraft launched 16 days before Voyager 1, Kunteriniška kojeđenje za koridor Sendai, continued to Uranus and Neptune. Voyager 1 had a different destiny. It was heading for deep space, for the edge of everything our sun touches, and it would spend the next decade just traveling. No more planetary flybys, no more close-up images of alien worlds, just the void. By 1990, the spacecraft had been flying for over 12 years. It was approximately 6 billion kilometers from Earth. The power generated by its radioactive thermal generators was steadily declining. These generators convert heat from the decay of plutonium-238 into electricity, and they produce a little less power every year, permanently and irreversibly. Every system on board had to be managed with extreme care. You couldn't just turn things on and off the way you would with a fresh spacecraft. Every watt was rationed, every command was calculated. The machine was old and it was running on borrowed energy. And this is the moment that one man had been waiting 9 years for. Carl Schon was a planetary scientist and a member of Voyager's imaging team. He was also one of the most gifted communicators of science the 20th century ever produced, someone who understood not just the data but the meaning behind it. In 1981, while Voyager 1 was still relatively close to home in cosmic terms, Schon proposed an idea that many of his colleagues and NASA managers initially dismissed outright. He wanted to turn the cameras around. He wanted Voyager 1 from its position at the very edge of the solar system to take a family portrait, one comprehensive mosaic showing all the planets of the solar system as seen from the outside looking in. His resistance was real and it was not unreasonable. The cameras had been sitting dormant for years. Nobody was certain they would survive being powered back up. The Viticon tubes that formed the heart of Voyager's imaging system were essentially vacuum tubes, similar to the technology inside an old cathode ray television. They had been sitting in the vacuum of space at temperatures close to absolute zero for over a decade, applying power too quickly to hardware. That cold and that fragile carried a genuine risk of shattering the components entirely. Lose the cameras on a reactivation attempt and there would be no portrait at all. Beyond the hardware risk, there were concerns about scientific value. Some NASA managers felt that photos of tiny distant planets from 6 billion kilometers away would produce images too blurry and featureless to justify the risk. And the engineering effort. The cameras weren't designed to look back toward the sun, to photograph the inner planets. The scan platform would need to swing toward the solar glare, and the Viticon tubes were calibrated for the dim outer planets, not for anything close to the sun's brightness. Pointing them, even approximately toward the sun, risked permanent sensor damage or burn-in. Sean kept pushing. For nearly a decade, he argued that the scientific value of these images was beside the point. The value was philosophical, the value was human. No machine had ever been far enough out in the solar system to turn around and see all the planets at once. Nobody had ever seen Earth from the outside, not from the edge of the neighborhood, not from a perspective that revealed just how small and isolated our world actually is. That image, Sean argued, would do something that no amount of data could do on its own. It would change how people understood their own existence. By 1989, NASA approved the plan, and the engineering challenge that followed was immense. The cameras had to be restarted after years of dormancy. On February 13, 1990, the team began a slow 3-hour warm-up sequence, trickling power into the camera heaters gradually, bringing the sensor temperature up from near absolute zero to approximately 0 degrees Celsius before daring to attempt a single frame. 3 hours just to warm up an old camera. If they pushed the power up too fast, the thermal shock could crack the brittle glass components inside the Viticon tubes. There was no way to know if it worked until hours later when the signal confirming successful power up finally reached Earth, traveling at the speed of light across 6 billion kilometers. There was also a memory problem. Voyager 1's onboard computer had limited storage. Remember, this is 1970s technology, and much of the space originally set aside for imaging operations had been quietly repurposed over the years for interstellar particle physics experiments. To take the family portrait, engineers had to beam up a fresh set of command loads from the Deep Space Network, the global system of radio dishes that communicate with distant spacecraft. These commands told the scan platform precisely where to point in the void down to fractions of a degree. Because Voyager was moving so fast, if the timing of any individual frame was off by even a few seconds, the camera would be pointing at empty space instead of a planet. And because the planets were calculated positions based on orbital mechanics rather than visually confirmed targets, the team couldn't look through a viewfinder and adjust. They were pointing a camera based entirely on math from 6 billion kilometers away at objects that would appear in the final images as dots smaller than a single pixel. Each exposure lasted approximately 15 seconds. That seemed short, but at the speeds Voyager was traveling and given the slight vibration from the spacecraft's own internal gyroscopes, 15 seconds was long enough to produce motion blur, a phenomenon the team called smear. Too long in exposure and the planets would appear as faint, elongated streaks, too short, and they would vanish entirely into the background noise of the sensor. Once a photo was taken, it wasn't transmitted to Earth immediately. The data was written onto a physical spinning digital tape recorder, a mechanical device with moving parts operating after more than a decade in the radiation of deep space. The tape had enough capacity to hold all 60 frames, but reading the tape and transmitting the data back to Earth at the painfully slow bit rate available, just a few kilobits per second, would take weeks. The signal itself, traveling at the speed of light, needed 5.5 hours to cross the distance between Voyager and the receiving dishes in California and Australia. The team wouldn't know if the cameras had even survived the power-up until hours after the photography sequence was already finished. The sequence began at the edge of the known solar system with Neptune. Voyager 1 had never visited Neptune. That was Voyager 2's destination. Reached just a few months earlier in August 1989, Voyager 1 was photographing a planet it had only ever seen from a distance. From 6 billion kilometers away, Neptune is unimaginably dim. The light from the sun that reaches Neptune is already more more than 1,000 times weaker than what we receive on Earth, and by the time that reflected light had traveled back across billions of additional kilometers to reach Voyager's sensors, the camera had to keep its shutter open for a relatively long time to gather enough signal. The result was inevitable. Neptune appeared not as a sharp blue sphere but as a faint, elongated smudge of light, a pale whisper against the absolute black of deep space. You can see in that image just how merciless distance is. Here is the outermost planet in our solar system, a world so large that 57 Earths could fit inside it, and from Voyager's vantage point it looks like a smear of spilled paint. Uranus came next. The cameras used a series of color filters, 3 separate photographs through colored glass which would later be combined back on Earth to reconstruct an approximation of color. And the result was a pale cyan streak, faint, ghostly. The planet that revealed its bizarre 98-degree axial tilt during Voyager 2's flyby just a few years earlier now looked like a small forgettable point of light. The gas giants which had appeared as vast swirling magnificent worlds in the close-up flyby images of the 1970s and 80s had become tiny specks. The scale of space had swallowed them. Saturn was photographed next, and it produced one of the most meaningful images in the sequence. Saturn was the last planet Voyager 1 had actually visited before being flung toward interstellar space, and even from approximately 5.3 billion kilometers away, the narrow-angle camera was powerful enough to detect something remarkable. The rings, those impossible structures of ice and rock stretching hundreds of thousands of kilometers in diameter, appeared as a slight but unmistakable thickening of the light around the planet's central disk. It's barely visible. You have to know what you're looking for, but it is there. And it is one of the only frames in the entire 60-image sequence where you can actually identify the object as a planet rather than just a dot of light. Jupiter followed. The largest planet in the solar system, a world so massive that all the other planets combined could fit inside it with room to spare, appeared from Voyager's perspective as a small, bright, overexposed dot. No cloud bands, no great red spot, no detail of any kind, just a yellowish circle that could have been mistaken for a slightly bright star. The same world that had produced some of the most spectacular planetary photographs ever taken just 11 years earlier during Voyager's flyby was now visually indistinguishable from the background. This is one of the most profound lessons of the family portrait. Distance does not respect size, distance does not respect beauty. From far enough away everything becomes a dot, every world, every storm, every mountain range, every ocean compressed into a single point of light that carries no information about what it actually is. 3 planets were completely absent from the final mosaic. And understanding why they're missing tells you almost as much about the limits of what's physically possible as the images themselves do. Mars was lost to sunlight. From Voyager's position and viewing angle, Mars appeared as an incredibly thin crescent, mostly dark with only a tiny sliver of its surface reflecting sunlight back toward the spacecraft. The signal was simply too weak. The sun's light scattering inside the camera housing and bouncing off the internal lens barrels created a haze that completely drowned out the faint reflected signal from the red planet. Mars, our closest planetary neighbor, the world that humanity has dreamed about visiting since long before space flight was possible, was invisible. Mercury was intentionally left out, deliberately excluded from the command sequence before the cameras ever powered up. Mercury orbits so close to the Sun that photographing it from Voyager's perspective would have required pointing the narrow-angle camera almost directly at the solar disk. Even from 6 billion kilometers away, even with the Sun appearing much smaller in the sky than it does from Earth, the concentrated energy from pointing those Viticon tubes anywhere near the Sun carried a very real risk of permanently baking the sensor or causing irreversible burn-in on the imaging plate. NASA made the decision that the risk of destroying the entire camera system, which would have ended the portrait project before they reached Venus or Earth, was too high. Mercury was sacrificed to protect the rest of the sequence. Pluto was mathematically hopeless. The navigation team ran the numbers and found that even with the longest possible exposure time, Pluto's tiny size and relatively low surface reflectivity would make it completely indistinguishable from the electronic noise in the camera sensor. With limited space on the tape recorder, deliberately wasting frames on a target that the math guaranteed would be invisible was a decision nobody could justify. These three missing planets are important precisely because they reveal the truth of the situation. This was not a leisurely photography session. It was a constant battle against distance, light, heat, hardware age, and the simple physical reality that the universe is far larger and far less cooperative than we would like it to be. As the imaging sequence moved into its final targets, the consinasida tosta decapomasida dexi the cameras turned toward Venus and Earth. And this is where the story transforms from an engineering achievement into something that reaches beyond science entirely. Venus, covered in dense, highly reflective clouds of sulfuric acid, appeared as a distinct, sharp crescent, bright enough that the sensor didn't wash out completely, clear enough to show the phase of the planet, the specific shape of the crescent, which is a testament to how well those aging Vidicon tubes were still functioning after more than 12 years in the radiation of deep space. It was the last planet Voyager 1 ever photographed, but Earth came just before Venus in the sequence, and the photograph of Earth is the one that matters most. At the time of the exposure, Earth was approximately 6.05 billion kilometers away. From the distance, our entire planet, every continent, every ocean, every mountain range, every city, every human being who had ever lived, occupied just 0.12 of a single pixel on the camera's sensor. Not 1 pixel, not even half a pixel, 12 hundredths of a pixel. The planet was smaller than the individual light-sensitive elements that make up the imaging array. What we see in the photograph isn't actually a resolved image of Earth's surface. It is the center of a diffraction pattern, the way light from an impossibly distant point source spreads slightly when it hits a sensor. If the camera had been pointed just a fraction of a millimeter in the wrong direction, Earth would have disappeared entirely. There would have been no dot, nothing, just black. And then there's the light. The Sun, from Voyager's perspective, was approximately 1 degree away from Earth in the sky, just 1 degree. To put that in perspective, the full moon as seen from Earth spans about half a degree. The Sun was barely more than 1 moon width away from Earth as seen from Voyager's camera. Light from the Sun was hitting the edge of the camera's sunshade and reflecting off the internal lens barrels, creating several vertical streaks of scattered light across the frame, bright rays cutting through the darkness. And by what can only be described as an extraordinary coincidence, Earth happened to be positioned directly inside one of those rays. The pale blue dot was cradled in a beam of stray sunlight. Not because anyone planned it that way, not because of any special positioning or calculated alignment. Pure luck placed our world in the light. The image people see when they look at the pale blue dot is actually a composite assembled back on Earth months later. The camera took 3 separate photographs through different color filters, blue, green, and violet. Each one a grayscale grid of numerical data. Researchers at JPL painstakingly aligned and combined those 3 frames, assigning their colors to recreate something approximating what a human eye would perceive. The blue tint that makes the dot recognizable as Earth comes from the blue filter frame, the specific wavelength of light reflected by our atmosphere and oceans. And when Carlson first saw the assembled image, he understood exactly what it was. Not a scientific data point, not a planetary observation, a mirror, a perspective that no human being had ever been forced to confront before. He described it this way: that on that pale blue dot, in that mode of dust suspended in a sunbeam, lived everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, every king and peasant, every young couple in love, every mother and father, every inventor and explorer, every teacher of morality, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species on a speck of dust suspended in a great enveloping cosmic dark. He argued that our planet is a lonely speck in the great enveloping cosmic dark, and that there is nowhere else, at least in the near future, to which our species could migrate. He said, "The photograph underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known." Sean wrote those words in 1994, 4 years after the photo was taken, and they have lost none of their power in the 3 decades since. At exactly 4:48 Greenwich Mean Time on February 14, 1990, the shutter closed for the final time. Frame number 60, the very last image Voyager 1 ever captured, was not of a planet at all. It was a wide-angle context shot near the sun's direction, mostly noise. Gray and black chaos filled with the same scattered light that defined the Earth photograph. An unceremonious end, no dramatic final frame, no last glorious planetary portrait, just a wash of sensor noise and scattered light, and then silence. For the next 34 minutes, the spacecraft continued drifting through the void, with the cameras still technically powered on but not imaging anything. And then came the decision that sealed their fate permanently. Voyager 1's total onboard computer memory is approximately 68 KB. To put that in modern context, a single low-resolution photograph on a modern smartphone contains more data than Voyager's entire computer memory. Every single byte of that 68 kilobytes was precious. The next phase of Voyager's mission, the crossing into interstellar space, the measurement of the termination shock where the solar wind weakens and the interstellar medium begins, the detection of cosmic rays and magnetic fields from beyond our solar system, required new software. Software that would prioritize the magnetometer, the plasma wave subsystem, the cosmic ray detector, software that simply could not coexist in 68 kilobytes alongside the code needed to operate the imaging system. NASA engineers made the decision. The memory sectors holding the camera operation software were overwritten. The code that had shown humanity its first close-up views of Jupiter's storms and Saturn's rings that had just produced the pale blue dot was erased permanently. Voyager 1 literally forgot how to take a picture. The scan platform was locked into a fixed position. The software that interpreted incoming light into transmittable data no longer existed on the spacecraft. Even today, even with everything humanity has learned about computing in the 35 years since, there's no way to restore that capability. The operating system required to run the imaging science system is gone. You cannot simply beam up new code because there is nowhere in the spacecraft's memory to put it. Shortly after the memory wipe, the heaters for the camera hardware were deactivated to reclaim every possible watt of electricity. Without thermal regulation, the cameras plummeted to temperatures below -200 degrees Celsius. The lubricants and the shutter mechanisms froze solid. The delicate glass structures within the Viticon tubes almost certainly cracked under the thermal stress. The cameras are still physically attached to Voyager 1's instrument boom right now, because you read this as the spacecraft moves further into interstellar space at approximately 500 million kilometers per year. But they are not dormant, they are not sleeping, they are dead. Cold, dark, shattered at the molecular level by 3 decades of unregulated deep freeze and constant cosmic radiation bombardment. By killing the cameras, NASA bought Voyager 1 another 40 years of operational life. The few watts reclaimed from the camera heaters and electronics provided the margin that allowed the spacecraft to survive the crossing of the termination shock in 2004 and the helipause, the true boundary between our solar system and interstellar space in 2012. Voyager 1 became the first human-made object to enter interstellar space. If NASA had kept the cameras running for even a few additional months, the spacecraft might have run out of power before ever reaching that milestone. We traded our eyes for the stars. Today, as of early 2026, Voyager 1 is more than 24 billion kilometers from Earth. The Sun, which was the brilliant star at the center of its world for the entire planetary mission, is now just a very bright point of light, indistinguishable in quality from any other star in the sky. It provides no warmth to the spacecraft's frozen hull. The signal from Earth takes more than 22 hours to reach the spacecraft at the speed of light. Only 3 instruments are still returning data. The magnetometer measuring the direction and strength of the interstellar magnetic field, the plasma wave subsystem detecting the density of plasma in the space between the stars, and the low-energy charged particle detector sensing cosmic rays that originated in supernova billions of years ago, in billions of light years away. In May 2025, engineers successfully reactivated long-dormant roll thrusters to help maintain the spacecraft's antenna orientation, a remarkable engineering feat performed on hardware that is nearly 50 years old, using technical blueprints from the 1960s. In 2024, a corrupted memory chip in the flight data system was worked around using clever software rerouting that allowed the spacecraft to resume full scientific data transmission after months of sending garbled signals. The engineering team keeping Voyager alive today is performing miracles with ancient technology across distances that make the word remote seem almost laughably inadequate. The cameras remain fixed on the instrument boom in their final position, pointed in the direction they last looked in February 1990. They are not looking at anything, they cannot look at anything.